Welcome to lecture 13. In this lecture, we're going to start with resistors with a parallel connection, and then we'll move on to do some examples where we have sets of resistors in both series and parallel together in a combination circuit. So just like we can have capacitors connected in series or in parallel, we can have resistors connected in series and in parallel. As a reminder, when things are connected in parallel, the tops are joined and the bottoms are joined. If you're trying to imagine what that means, so let's say we take our first resistor R1 and we take a set of leads and we plug it into the battery. That means that the potential across resistor R1 is the same as the potential across the battery. Then for our resistor R2, we connect those up to the battery as well. That means the potential across R2 is also the same as the potential across the battery. And then we take R3 and we hook that up to the battery. So that has the same potential as the battery. So when things are connected in parallel, they all have the same potential difference. They all have the same voltage. We can draw equivalent circuits. An equivalent circuit is one where we take out the resistors we have in parallel, we put in a new resistor, and that gives us a current, a circuit that's driven by the same potential. It delivers the same total amount of current from the battery, and the resistance we call R equivalent. It's equivalent to some combination of resistors R1, 2, and 3. So if we draw an equivalent circuit, it has the same potential, delta V, it delivers the same current I, and it has a new resistance called R equivalent. So in our circuit on the left-hand side with the three individual resistors, an amount of current I comes out of the battery. In our equivalent circuit on the right-hand side, that same amount of current I comes out of the battery. So that's what happens in our parallel connection. So let's think about what happens to that current I. Remember, a current is a flow of charge. So the current I in our left-hand picture, it comes on until it hits this junction. So you see that two wires branch off of this point. That means that the charges have two choices. They can flow straight or they can flow down. The amount of current that flows down, we'll call that I1. Okay, the amount of current that flowed straight, well, it hits a junction and it's got two choices. It can go straight and down around through R3, or it can bend down and go through R2. The current that goes down through R2, let's call that I2, and then the last current that goes through R3, we'll call that I3. And then we further know that R1, 2, and 3 all have the same potential because they're connected in parallel. So I'm going to label that bit in on the diagram, that they all have potential delta V. So let's write down what we just said about current, which is that our current I splits over three paths. Now that current can't leak off anywhere, so it can't escape. Therefore, that the total current has to be those three currents added up. Okay, because we can't lose current and we can't gain current. So let's layer in our Ohm's law here, remembering that Ohm's law says that the net potential is equal to the current times the resistance. In terms of current, it means that current is the potential across an object divided by the resistance of the object. So let's apply this now. For our net current I, let's come over to our right-hand circuit. We see that through our equivalent resistor, current I will flow. The equivalent resistor will have a net potential delta V across it. So if we look at all these three things together, we know that the current is equal to the potential across that resistor divided by the resistance. Let's fill that in on the left-hand side of our equation. And that delta V refers to the same amount of potential supplied by the battery. Okay, let's come to our left-hand picture and look at I1, I2, and I3. I1 is the potential across resistor R1, that's the same as the potential of the battery, divided by resistance 1. I2 is the potential across resistor 2, delta V, same as the battery, divided by R2. I3 is the current through resistor 3, that's equal to the potential across resistor 3, which is the same as that supplied by the battery, divided by R3. We know that our potentials are all the same, so we can divide through by potential. And what we end up with for a final expression is 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. If you had more resistors, you'd do 1 over R4 plus 1 over R5 and so on. So this is how we add up resistors in parallel. Here I would just throw in a tiny bit of caution. So far we've done capacitors in series and parallel and resistors in series and parallel. Capacitors in parallel, you add them up, C1 plus C2 plus C3. Resistors in parallel, you add up the reciprocals. Capacitors in series, you add up the reciprocals, and resistors in series, you just straight up add them, R1, R2, and R3. So just be careful you don't get confused with your rules of addition as you're going through the different types of circuit elements. In this example, we have a set of resistors in parallel, and we'd like to find the equivalent resistance, the current through each resistor, and the potential across each resistor. Before we get started, I'm going to label that the battery has potential delta V. 60 ohm resistor is R1, the 20 ohm resistor is R2, and the 10 ohm resistor is R3. So now if we use symbols, we'll know that we're good. I think I'm going to do part C of this problem first. It asks for the potential across each resistor. These three resistors are in parallel with each other and with that battery. That means all those things have the same potential. So we have a parallel connection, which means same potential. I don't have quite enough room to write the word potential, so I'll use a little bit of shorthand. So delta V across resistor 1 is the same as that as across resistor 2, same as that across resistor 3, which is the same as that of the battery, which in the diagram is given as 9 volts. I'm going to label that in my picture. 9 volts, 9 volts, 9 volts. If I had lots of room, I'd probably go with 3 sig figs here and write 9.00, but I don't have a ton of room. Okay, next we can do A first or B first. Doesn't really matter. We're going to do those kind of independently. Let's go ahead and do A just because A comes before B. So if we want to find the equivalent resistance, we'll draw an equivalent circuit. So we put in our battery. The long line means the positive end. The short line means the negative end. We pop it at the 3 resistors, and we put in a new resistor with an equivalent resistance that we label REQ. We're trying to find that equivalent resistance. We'll use the rule that we have for when we add resistors in parallel, which is that 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3. So we've got 1 over 60 plus 1 over 20 plus 1 over 10. If you're a numbers person, you can go ahead and do numbers. If you're a fractions person, you can go ahead and do fractions. I'm more of a fractions person, so 1 over 60 plus 3 over 60 plus 6 over 60. Oops, I said 60 and I wrote 10. Gives us 1 plus 3 plus 6 is 10 over 60. Then to find our equivalent resistance, we take the reciprocal of both sides, so 60 ohms divided by 10 to give us 6 ohms. So our equivalent resistance of this entire circuit is 6 ohms. Kind of interesting that when you add things in parallel, the equivalent resistance goes down. Part C,
find the current through each resistor. So we'll use Ohm's law for this part. Ohm's law says V equals IR. That tells us that each current I is going to be the potential divided by the resistance. So I1 is delta V, the potential across resistor 1, divided by R1. So 9 volts over 60 ohms. That gives us 0.15 amps. I2 is delta V over R2. 9 volts over 20 ohms equals 0.45 amps. I3 equals delta V over R3. 9 volts over 10 ohms gives us 0.9 amps. Okay, a couple of interesting things just to point out here or to notice here. If you added up all of these currents, you would see that this was equal to 1.5 amps. And then you might also notice, if you looked at your equivalent circuit, that the net current put out equals the change in potential over R equivalent, 9 volts over 6 ohms, you would get 1.5 amps. Okay, the problem didn't ask for the net current, but it is good to see that all these things work out. So the net current you can find in the equivalent circuit, or you can just add up all the three currents through each resistor. So I think I'm going to add those currents to my picture, because then I'd like to discuss that just a tiny bit more before we move on. If you look at the currents, you see that the biggest resistor, 60 ohms, has the smallest current, 0.15 amps. The smallest resistor, 10 ohms, has the biggest current, 0.9 amps. This makes sense when you think about what resistance means. Resistance means resistance to current flow. If something has a high resistance, it's hard for the current to get through. So then when the current picks its path as it goes through, so your current comes to this junction, some is going to move on and some is going to go down through resistor R1. It's hard to get through R1, so not much current goes down through that branch. Then we get to the next junction, some of it moves on and some of it goes down. It's hard to go through R2 because that resistance is bigger than R3, so less of it goes through R2. So that's a good way just to stop and take stock of your answer after you find it. Does it make sense logically? What I've got here is a clip from a PhET simulation of a circuit analysis. So I've reproduced what we just did in the previous slide. So I've got a battery and I'm going to start to construct that parallel circuit. If you want to do this for yourself, then by all means, I absolutely encourage it. If you Google PhET, P-H-E-T, circuits, your first hit should be this kind of circuit construction. It's a little bit fiddly to stick the wires in there, but it's not difficult to do. So you'll see I got my first resistor in place and the current is starting to flow through. I'm going to put in more wires and put in my next resistor. And you'll see that I'm getting all those connected in parallel. All the wires we assume have zero resistance, so we don't get much potential drop over the wires. And it means that all of our resistors have the same potential across them because this is a parallel connection. All the tops are connected and all the bottoms are connected. Okay, there's my circuit all complete now, current going through each branch. The battery is 9 volts, 60 ohms, 20 ohms, and 10 ohms. First thing I'll do is I'll use my voltmeter and I'll measure the potential across each of my elements. So I've got my 9 volts there, 9 volts here, and 9 volts here. And just for good measure, we'll do it across the battery as well, also 9 volts. Okay, next let's grab the ammeter and let's measure our currents and see do they match up with what we found. So through R3, our current is 0.9 amps. That's what we found when we did our problem. So I'll just take the ammeter back out. Like I said, this is a wee bit fiddly. Okay, I'm going to put my connection now in with R1 next, my ammeter in with R1, and 0.15 amps, that was what we got when we did our calculation. Okay, pop out my ammeter. To reconnect my circuit, if I don't completely reconnect it, then I won't get the same answers. And I'll put it in with my R2, 0.45 amps, which is what we got when we did the calculation. So it's good that the simulation is backing up what we anticipated. The next thing I'll do now is I'm going to construct that parallel equivalent circuit. So remember, the parallel equivalent circuit has a battery with the same potential. So I'll grab another 9-volt battery. And then I'm going to make a circuit where instead of having 3 resistors, I have a single resistor. And remember, when we did our calculation, the equivalent resistance turned out to be 6 ohms. So that's the resistor I'm going to stick in there. So there's a resistor. I'll click on it, set the resistance at 6 ohms, and then I'll put that in my circuit. And I have to connect it to the battery with a wire. So we see that we get that net current flow of 1.5 amps, same as put out by the battery in the previous part. And you get the same potential of 9 volts. So these FET simulations can be real nice just to help you verify that you got the right answers when you did your problem. Let's do another quick example, but just a slightly different twist on it. Let's say we have 3 resistors, and we can see that they're all connected in parallel because the top of the 10 ohm goes to the top of the 15, which goes to the top of that one R. The bottom of the 10 ohm goes to the bottom of the 15, which also goes to the bottom of the R. So they're all connected in parallel. We want to find the value of that resistor R. So what's that guy going to be equal to? Right off the bat, we know that things in parallel have the same potential. So for our resistors, the 10 ohm resistor has a potential of 8 volts across it. The 15 ohm resistor has a potential of 8 volts across it. And our unknown resistor also has a potential of 8 volts across it. Well, let's ask what can we do from here? If we remember Ohm's law, which says that V equals IR, then we know that the current through any resistor is the potential across it divided by the resistance. So for our 10 ohm resistor, the current through it is 10 ohms divided by 8 volts. Oops, I got that upside down. Sorry, I'll fix it. It's the potential, 8 volts divided by 10 ohms equals 0.8 amps. For our 15 ohm resistor, the current through it is the potential across it, 8 volts, divided by the resistance of it, 8 over 15, which is equal to 0.533 amps. I'm just going to label that up there on my picture because I like to have all those things really nice and together. Now, we know the current through the 10 and the 15. We don't know the current through the R, or do we? If we look up at our picture, we see that we have 2 amps coming in. We think about what happens to that current. Part of it goes through the 10 ohm, part of it goes through the 15, and part of it goes through R. And we know we don't lose or gain any current. Therefore, 2 amps has to be equal to 0.8 amps plus 0.533 amps plus the current through that resistor R. So our current through that resistor R is 2 minus 0.8 minus 0.533 to get 0.667 amps. I'll label that on my picture. Well, now if I look at that resistance R, I know the potential across it, and I know the current through it. Therefore, I can definitely find that resistance. If V equals IR, then R is equal to V divided by I. The potential across R is 8 volts. The current through R is 0.667 amps. That tells us that that resistor has a value of 12 ohms. So R is equal to 12 ohms. Now our workings got a little bit messy, but hopefully you could understand all those steps as I went through it.